Welcome everyone to this series. It's good to see people face to face again, actually. I'm here to introduce Professor Gianluca Iaccarino, who is a professor in mechanical engineering and director of the ICME, the Institute of Computational Mathematical Engineering at Stanford University. He received his PhD in Italy from Politecnico in Bari, in 2005, and worked for several years at the Center for Turbulence Research before joining the faculty at Stanford in 2007. Since 2014, he is the director of PSAP Center of Stanford. Also, two directorships. Director Square, funded by the Department of Energy, a large research center focused in multiphysics simulation. Now, something that you do not know about Gianluca that is not in his bio, right, is that he and I were office mates together at Stanford University, right, when we were postdoc at the Center for Turbulence Research, which he never put in his bio, apparently. So I am not very happy with that. But one thing about Gianluca that you should know, right, and this is something that I'm very jealous of, right, in 2010, he received the Presidential Early Career Award for Scientists and Engineers from President Obama. So if you go to Gianluca's office, right, you see a photo of him shaking hands with President Obama. And I'm very, very jealous of that particular photo. So Gianluca, what I want to do today, right, is that I want to shake your hand, right? And I want you to take a picture, right? And I want you to put this picture, right? I want you to, no, I want you to replace the picture with this picture. I told you. All right, so Gianluca has been a great friend of mine for many, many years now, and he's been working on uncertainty quantification. And he's going to be here talking to us about that.
Thank you, Andrew, and thank you all for joining. It's a real pleasure to be here. Okay. Just a moment. So I've been spending some time here in Melbourne, and I enjoyed it tremendously. I go a long distance in terms of experiences and so on with Andrew. So it's been a real pleasure to be here working with his students and working with him on various things. What I'm going to do though today is to give you a sort of an historical view of some of the large projects I've been involved in at Stanford, basically since Andrew left, which is kind of interesting. It's all happened basically in the last 10 or so years. The talk is very high level, so just a few details. There are equations just in a couple of slides. But I hope you'll find it interesting, especially assume that this is all most of you are involved in fluid mechanics. So I try to emphasize more the fluid mechanics of some of these projects, but there are other aspects that are critically important and perhaps will pique your interest as well. So as I said, it is a sort of a retrospective on a sort of history of simulations, especially simulations of turbulence at Stanford, and it goes way earlier than when Andrew and I were in that office at CTR. So this was at least from this perspective goes down to the 80s, the late 70s, early 80s, when a fairly important paper was published. This is one of the most cited papers in the fluid mechanics community, is from Professor Parviz Moin and Professor John Kim. It's the latest of a sequence of papers where they started to publish work in numerical simulation of turbulence, and as I said, in the 80s. And what is interesting about this paper is that it was the first time that detailed simulation of turbulence were actually presented at the American Physical Society. This is actually the movie that Parviz and his group showed at the conference. And before that, it was not really that common to think of numerical simulation as being very much a very, very close sibling to experiments. So this is a vertical wire. Again, it's a numerical simulation. You'll see a channel, so two parallel plates. It's an incompressible flow, and they're basically tracing particles or numerical particles from the inlet of these flow all the way through, and you can see sort of structures that remind you, if you've been in a lab, and obviously you have great experimental facilities here, you sort of see structure that look very much like the real turbulence you expected to see in a lab. Now, what's interesting about this? You see that it's a little wobbly. The movie itself. Remember, this is sort of a vintage from the archives of fluid mechanics. The movie was actually taken by Parviz and his group, taking pictures of a screen of a computer, right? Picture after picture, and then mounted as a movie. So this is really the beginning of everything we do today, with a lot of hard work behind. But I want to fast forward this. Now, this was the 80. Fast forward 20 years. I'm not going to tell you too much about the first 20 years, but the 20 years later, we were doing this simulation. Basically, when Andrew and I started at Stanford, this was just few years afterwards. Numerical simulation of an end-to-end jet engine. So all the components, all the rotating components, all the physical processes that occur in the combustion chamber, all simulated as one big coupled simulation. And again, this was in the 2000s, so 20 years ago. You see that obviously the quality of the movie has improved, but also the sort of complexity of the problem is increased by order of magnitude. Is a very, very challenging simulation still today to do this kind of simulation, but now they're starting to become common practice in industry, actually, to take an entire device and simulate it with the physical processes that are occurring. Turbulence is obviously a major player here, but you start to see within the combustion chamber, you see here, multi-phase flow combustion, all these processes are actually simulated as part of this process. So what is that I want to do is to sort of give you a sense of how this happened and why we started from a channel flow, we ended up doing simulations of a jet engine, but then also what happened in the last 15 years or so since these calculations. So the first thing to keep in mind is that advanced simulation and computing is not my title. It's not a sort of a generic way of describing the simulation. It's actually a program started by the US Department of Energy, a very, very large program, started in 1995. And the main goal, or one of the principal focuses, was to shift from test-based confidence into simulation-based confidence. So you might not know, but the Department of Energy of the United States is actually in charge of all the nuclear devices in the United States, including the submarines, the weapons, everything that has to do with nuclear science is actually part of the Department of Energy. And as you know, in 1995, there was a nuclear test ban where nuclear devices could not be tested in physical experiments. So everything related to the certification of the devices, if they're still working, if they're safe and so on, has to be based on simulations. So this was the sort of start of advanced simulation and computing, a framework that allowed scientists in the national labs, and we're talking about thousands and thousands of scientists, to actually use simulations. How Stanford's coming to the picture is because as part of this very, very large program, and we're talking about hundreds of billions of dollars every year, the Department of Energy invests a small part into academic alliances with universities to run large-scale projects, but still in a university. They have nothing to do with nuclear devices. Actually, the ingenious part about the Department of Energy is that they ask the university to pick a problem, and the problem can be of any sort as long as it has some characteristics. And it turns out Stanford is the only academic center that has been in existence since the beginning for 20 plus years. So every 5 years, we have to write a new proposal, submit a new proposal, go through the competition. But the idea is that we have been sort of moving along the Department of Energy for the last 20 years. And what I want to tell you is a little bit about some of these projects. The key elements that is common in all these projects are these four elements, and I'll unpack what this means in a moment, but this is just to start by telling you that there are very different problems we work on, but there are very common themes within these projects. So what are the projects? As I said, I already sort of mentioned the first one, which was actually the longest, was 10 years long. And it was the simulation of the jet engine, including all the moving parts, the reacting flow, and so on. This was, as I said, the first demonstration that you could do simulations of this sort. And it turns out, in fact, after this program, the ASC program changed the focus and said, we know now that effectively you can simulate anything you like, right? Given enough resources, enough, experimental evidence and so on, we actually can do the simulation. So the question is, can we believe the simulation? And that sort of a shift in the program was really, in 2007 or so, when we started the program that are called PISA programs, which are the ones that I've been mostly involved in. So we went from a jet engine to a high-speed combustion engine. This is an hypersonic combustion system. It's a scramjet that we were simulating in that second project. The third project shifted completely. We went to a solar energy device, in particular a particle-based solar receiver, which I'll tell you more about in a moment. And the other elements, so these are the problems. So you can see that fluid mechanics is always important, at least in our problems. We sort of picked turbulence and fluid mechanics as a critical, foundational element. But the other piece that is common in all these projects, and actually was common also when Professor Moyni started the first simulation of the channel flow, was the computer science element. It turns out that along the way, we ended up working on very, very different computers as we progress. And these computers push the envelope of what the simulation capability needs to be able to use them. And the other sort of element that I think, again, is worth mentioning is that the Department of Energy in this program not only invests into software capability, but also the hardware. So it turns out the Department of Energy owns many of these machines. Many of the largest supercomputers in the world are actually part of the US Department of Energy. So in working on this project, we also had the opportunity of actually accessing some of these machines very early on and being able to really invest in the research that would help us achieve performance on some of these massive supercomputers. The project on particle-laden turbulence was finished about a year and a half ago. And the new project that we're working on is a project related to ignition in solid rockets. And this is sort of the current activity, the one that we are very, very much engaged in right now. So I'll tell you, I'll focus my next 30 minutes or so on discussing these two projects. I will skip the previous one, although there is a lot of really interesting aspects of those projects too, but I'll obviously try to give you a little bit more details of these two. But before doing that, as I said, I want to unpack these four elements, especially for the benefit of perhaps the younger students here that might not be neither familiar with what the keywords here mean, but also what is the reason why we're doing this kind of large-scale projects. So the first is the overarching scientific challenge. And the basic idea, as I said, is the Department of Energy is not asking us to work on a specific problem, is asking us to come up with a problem that has a very clear question, and the question should motivate simulations beyond what we know already. So that's a very sort of simple statement, but the key idea is that you have to be extremely intentional in how you formulate that question, because for 5 years the Department of Energy will come back, and we have reviews every twice a year, every 6 months, asking where are we, how close are you in answering that question. So it's a very important element of those projects, and I'll show you what the questions are for the two projects that I'll present. The second, as I said, is multiphysics process, and this simply means that you need to capture in a sense multiple processes that are coupled and interacting together. So, for example, the simulation of a channel flow is a very complex problem in turbulence, but it is clearly a single physics problem, right? The fluid is interacting with wall, turbulence is generated, there are multiple scales, a very complicated nonlinear problem, but it is a single, well-defined physics problem. What the problems we need to worry about in this picture for this project have to do with multiple physical processes interacting together. And the reason why that's critical is because every time you have multiple elements, multiple physical processes at play, then there are choices you have to make in terms of modeling. What is the modeling of each single one? What is the modeling of the coupling? And simplification that might lead to important assumptions and perhaps errors in those simulations. And so that's part of the reason why multiphysics is so important. And we use the keyword multiphysics as Department of Energy does, but think of it as turbulence plus X, at least in our problems. The third one, as I mentioned, is high performance computing. You know, Department of Energy is focusing on development of also the hardware platforms, and so the projects sort of follow along. And over the last 20 years, we've been working very closely with computer scientists at Stanford to develop capabilities that are innovative, and I'll give you a very quick example of that. And then the final, and perhaps the most important, is predictive science, which is really the idea that we don't just want to do simulation. We don't just want to demonstrate that you can do a simulation that is, you know, that looks realistic. You want to have an understanding of the confidence in those simulations and the outcomes of those simulations. So my plan for the talk is really to give you 4 mini stories, in a sense, that move from the first physics problem, which, as I said, is a solar receiver, to the last physics problem, which is this ignition scenario in a high altitude rocket. So let's start at the very beginning, obviously, and the first one. And the motivation for this, the overarching question is in the context of solar receivers. I don't know how many of you are familiar with solar receivers. This is an experimental facility in the Nevada desert, again, part of the Department of Energy. And the way it works is that you have an array of mirrors, an heliostat field that concentrates solar light on this tower, right? So there is if I actually turn around the tower itself, there is a big, you know, that big concentrated radiation that hits the tower itself. So at this point, you have an enormous amount of radiative energy available, and the question is if you can do something about it, something with it. The typical device that they use, at least in this facility, is what's called a particle receiver. So you have basically large sand particles or other material that are exposed to this radiation, to this very highly concentrated solar radiation through a window, and obviously get heated quite quickly and quite to a very high temperature. And then these particles are basically stored as a potential source of energy. And then eventually there is an additional transfer mechanism that moves this energy to a fluid, and then you can use that fluid in some sort of a heat transfer device in a thermodynamic cycle. So this is the system that I've been using, and it's a system that basically works, is effective. It has some limitations, but is a system that allows storage of energy for future use, basically. At least that is the facility that they've built. Our idea and our overarching question was, can we transfer directly the energy to a fluid, in particular to a fluid we're very used to work with, to air, and then use that fluid heated because of the radiation input that is available directly in the thermodynamic cycle? Can we build a system that, rather than store the energy, will use it directly in the thermodynamic cycle? So the basic idea is that if instead of particles you have air is transparent to radiation, you get nothing, right? Basically. So what you need to do is to have a medium within the system, within these passages that absorbs the energy and then transmits it to the fluid very, very quickly. And so what we decided to use, or our question was, can we use small particles, very, very small compared to the other one, that interact with the fluid flow and that transfer the energy very quickly? So they absorb radiation and they transfer to the fluid. But in addition, because we know that particles and turbulence interact, if there is a very highly active turbulent flow, what we can do is that we can actually see that this particle will start concentrating in certain regions. I'll tell you a little bit about that in a moment. And then we can have actually very, very high absorption of energy locally and increase the efficiency of the system. And then turbulence also allows us to mix that energy very, very quickly and so get to a very high efficient system. So that was our question. Can we actually do that? And again, the point is that we are not going to be able to do large scale experiments, or at least not very quickly. So we want to do this mostly computationally. Now, it is a multiphysics problem because, as you might know, and many of you might be expert in this field, typically the way we represent turbulence and fluid flow and particle flows use very, very different computational approaches. So on one end, you use an Eulerian model. You have, the partial differential equation solved on a grid. For particles, you typically trap them in a Lagrangian fashion. So now all of a sudden, you have already two very different methodologies that you have to implement, have them coupled, and then use on a supercomputer. In addition, here we have radiation. And radiation obviously is a first-class citizen in this problem. We have to model both the absorption into the particle, the scattering, and then eventually be transferred to the fluid. And radiation modeling actually uses a completely different strategy for computational purposes than the other two that I mentioned before. And so we have a very, very complicated coupling of very different numerical methods that all have to be coupled and ported on a very large parallel computer. So that's the challenge that multiphysics poses on this simulation. Now let's go back to the physics, because again, this is mostly a physics community, a fluid community here. As many of you know, the modeling of particle-laden turbulence is modulated or is governed by the Stokes number, which is really just a ratio of time scales of particles and the fluid flow. And it turns out that when that Stokes number becomes close to unity, interesting things occur, that the interaction is actually quite interesting and quite complex. So what happens is that preferential concentration emerges. So what is preferential concentration is that if you start from a uniform laid particle system, so particles are everywhere in your system, because of turbulence and because of interaction of particles with flow structures, vortices and shear regions in particular, you actually have regions that are voided of concentration, basically no particles, and regions that are actually very highly concentrated. So this preferential concentration is something we want to use to improve our ability to absorb radiation so that we have more and more efficiency in that. And as I said, there is a lot of evidence that this occurs in fluid mechanics. These are just a couple of examples. And perhaps the image on the right is the most interesting. This is a jet at the same Reynolds number, a particle-laden jet. And as you can see, as you change the Stokes number from very small to very large, Stokes 1 is somewhere in between, you start seeing very, very different structures that are captured by the particles, which means that, effectively what's happening is that preferential concentration leads to particles being much more concentrated in certain areas instead of others. So this is, as I said, all very well known. And actually, from a physics perspective, we also know that when you have a system with particles and fluids in turbulence, what happens is that turbulence tends to be reduced, or the kinetic energy in the system is actually reduced as a function of the mass loading. As you increase the mass loading, there is more and more transfer of energy between the turbulent fluctuation and the particles, and you tend to lose turbulence in a sense. And this picture, as I said, is very well known, but this is not what we're simulating. We're simulating a system where you have continuous injection of energy in the system. Right? There is energy in the form of radiation that is absorbed by the particles. And so the question is, what is the fate of turbulence in that case? And that question is actually not very well understood. It turns out that the physics of the, oops, oh, I'm looking at the wrong picture. Okay, the physics of the coupling is actually much more complicated. You have energy input that goes into the particles. So the fluid is assumed to be completely transparent from radiation perspective, but then the energy is actually coupling everything, coupling the fluid and the particles again. And the question again in this case is, are we seeing the same sort of turbulence modulation when we get to Stokes equal 1? The particles are start to kill basically the turbulence, or instead can we self-sustain these mechanisms? And this is obviously very important for our question of the solar receiver, because if turbulence is going away, we're not going to get mixing, and we're not going to get a very efficient system. We're just going to get spots of high temperature, but not a very uniform distribution of temperature in the system. And so we have been doing simulation of these, try to understand what's happening. This is a simulation in a turbulence box. You see temperature and particle concentration. So what you can see is that very quickly, and that's a time history of the kinetic energy in the system, very quickly, this homogeneously distributed particle system becomes very highly concentrated in certain region, preferentially. The purple area you see are very high concentration, obviously. And this leads to extremely high intermittent events in terms of temperature fields because of the wakes of these regions that are created that create a lot more mixing. And as you can see, though, turbulence does not decay. The turbulent kinetic energy remains basically in a constant state. So we can actually inject just enough energy to keep this system from decaying in terms of turbulence. So this is the first time we observed this, and obviously this is, in a sense, the starting point of the entire project. Because this happens, then there is even a point of trying to build a particle receiver like the one that we are considering. But this, as I said, is a simplified system. We also did experiments in a lab. This was Professor Eaton's vertical tunnel, where we have basically fluid and particles that are subject to a very high radiation source. In this case, obviously, it's not sun, but it's not the sun, but is a apparatus in the lab. But the interesting thing about this experiment is that Professor Eaton was able to measure at the same time velocities, temperatures, and radiation absorptions in a sense. So all the three sort of elements that are part of the multiphysics system that we have are actually measured at the same time and then compared to simulations. And so we can actually start to build some confidence in the simulation by doing this comparison. Without going in details, I'll just show you the first one, which is the temperature profiles obtained at the exit of this experimental facility, both with experiments and simulations, and at different values of mass loading. So as you increase the number of particles in the system, starting from 0, which is the dashed line, to higher and higher, you see that the delta T, which is the temperature increment in the fluid, increases. So the particles are able to transfer more and more energy to the fluid. But you also see, first of all, you see that the locations 0 and 1, that are basically the walls, are very, very high temperature. And this has to do with a number of phenomena, in particular, the fact that particles tend to become concentrated close to the wall, and so they absorb more energy, and that energy heats up the fluid in those regions. And that's obviously problematic in practical terms, but it's not really the critical component of the system. The critical component is the increase that you have at the center line, which means that as you overall increase the loading of particles, you get more and more overall transferred to the fluid, and so the fluid is heated and eventually can be used for other purposes. So the system itself is working, at least in principle. But the other thing that you notice here is that the simulations and the experiments are not very, very close, right? The simulations are predicting, as you increase the mass loading, are predicting a more turbulent profile, in the sense that is flatter in the sense than in the center than in the experiments. And that discrepancy is obviously something that is now asking or creating the question: are we able to do we believe these simulations or not because of this discrepancy? What do you do to understand that discrepancy? And just to give you an idea, obviously this is a short version of the long story of the project. It turns out that the simulations and experiments have a lot of differences. There are a lot of assumptions we have to make in the simulations that don't really have a counterpart in the simulation, in the experiments. So, for example, this is one of the most critical one. On the left is the ideal scenario we would like to simulate, where you have particles injected that are all the same size. Right? They are exactly 11 micron nickel particles that we're using in the simulations. And the result is basically a distribution of temperature at the outlet, which is the temperature of the fluid that we obtain at the outlet. In reality, the particles are coming from, manufacturer, and they have, more or less 11 micron diameter, but not quite 11 micron. So it turns out we have effectively a distribution of particles that is being fed. Many are smaller, some are larger than 11 micron. And this actually introduces a change in how the mixing and heat transfer occur. And so this is something that, again, needs to be captured if you want to really compare the simulations experiment properly. There are many more sources. The other is the radiation source. As I said, we're using lamps in it's actually a diode array. It's a fairly complicated system that Professor Eaton built. And it turns out the assumption is that it's a monofrequency, all collimated light, very, very clearly, very closely specified. It turns out there are a lot of impurities and a lot of distortion in that input source. And so the chamber is actually subject to a non-uniform radiation input rather than a very, very clear radiation source. And then there are other aspects of the simulations and many more than this. But one, for example, is what we do with collision and deposition of particles. This is effectively a dilute system. So we don't really typically worry about collisions between particles. They're very, very seldom occurs. But it turns out that close to the wall, the concentration increases and increases to a point where collision actually becomes inevitable. And so not modeling collision, especially near the wall, changes substantially what is the concentration of particles. And so that's a model that needs to be included in the simulation that is obviously not a model that you need in the experiment and creates differences. And so on and so on, you have a lot of sources of uncertainties. So let's talk about a little bit of what we do with uncertainty. I mentioned a number of things, and this is an interesting picture that shows what is the actual uncertainty in the particles. So the picture on top is the powder that we get. These are, if you just look at them, but the manufacturer actually gives us a bottle like that with the probability distribution of the actual particle size, believe it or not. So they, although we are trying to buy 11 micron particles, they give us that. And then it's up to us to see what we do. And it turns out that after you go through uncertainty quantification and so on, you realize that particles are just a primary source of uncertainty. Then what we do is that we take the particles, and our graduate students actually, use a filtration system to actually go down to a much, much finer distribution of particles, much closer to 11 micron than we originally went, right? So the idea of uncertainty quantification is also to improve our ability to control some of these uncertainties, not necessarily just live with them. And I mentioned a few other things like wall particles interaction and so on. So what do we do with uncertainty? Well, the first step, as I said, is just identify which one they are. And when we started the project, we had we call it the master book of uncertainty. There were hundreds of uncertainties in that master book. Now, obviously, as you go through the project, you start learning about some are either very small or they're not very active. And so you sort of start to reduce them. It turns out that the last iteration of these, we had 14 uncertainties, okay? And what they are basically representation of some of the input in the simulations that we simply cannot pin down to a single number. Just to give you an idea, for example, number 9 and 10, right? These are the particle absorption and scattering coefficient, right? We cannot just pin down a number for those, and so they remain like an interval or a range of possible value, and so for everything else. At this point, we have uncertainties. What we do is that we perform simulation rather than on a single condition. We actually extract realization of those 14 variables, and for each one of these realization of that, sort of 14-dimensional vector, we run a simulation. And so we run, hundreds of simulation. We build an empirical distribution. Effectively, we build statistical analysis, statistical summaries, and confidence interval. And that's sort of the process. Now, how we do that, I promised one slide of equations. This is not different from what we do in every other field where you really cannot pin down exactly what's happening. So in weather, in meteorology, this happens all the time. So what you do is that you run independent simulation or independent trajectory, and then you average them and get some sort of statistical mean, what is the most expected, in this case, trajectory for an hurricane, and what is the confidence interval. And what's mathematically behind this is simply the concept of Monte Carlo. So the idea is that this is an empirical distribution that you're constructing, and so you can get estimate of statistics, for example, the mean, in that case, the expectation. But more importantly, you have a very clear, at this point, definition of what is the confidence. You have an error estimate for that, an error for that estimate, which is written here, which is proportional to the variance and inversely proportional to the number of realization of that trajectory that you build. And again, this is, statistics 101. But why is this really relevant, and what's the challenge here? Is that the cost of actually performing this estimate is directly proportional to how many simulations you run. And I didn't tell you this before, but each one of these calculations can take a week on hundreds and hundreds of CPUs. So we're not going to run 1,000 of these calculations, or not even 100 typically. So the question is, okay, this is what we want to do, but we can't afford to do it. So what do we do? Well, there are, again, hundreds of approaches that have been developed to go faster than Monte Carlo, to be more efficient than Monte Carlo. I'll just show you one idea to connect it back to what we're doing, which is Controlvariates. So the basic idea is very simple. Rather than, if we're trying to estimate Q, in our case, the efflux of the system, rather than estimate it directly, we can actually compute another quantity, P, of which we know the statistics. And it turns out that if P and Q are correlated, if there is a direct correlation between the two, the error, in this case of the estimate, is actually not the same error as before, V, the variance over N, but it has that pre-multiplying factor 1 over rho squared. And rho is basically the correlation between the two quantities. So it turns out if they are very, very well correlated, if rho is close to 1, you can imagine that the error in that estimate is obviously much, much smaller, right? And so the basic idea is that if we can build an estimate of our quantity of interest, we can do the Monte Carlo sampling with much less sample and being very small, but still with very, very high accuracy. And it turns out that that's, as I said, this provable theory is not something that we invented. It's very, very well understood. But the big question is, what is P? What is that is well correlated with the flux? And that's a $1 million question. It turns out in what we do, a good estimate for P is simply, quote unquote, a coarse estimation, a coarse calculation compared to the previous one. It's not going to be very accurate in absolute manner, but as long as it's correlated, it's useful. And again, there is a lot of theory, a lot of good results on this kind of methodology. What is the challenge in our case, though? Well, the challenge is, what does it mean to do a coarse calculation in our setting? You can be coarse in many, many different ways. You can do spatial, temporal coarsening of the turbulence. You can use less particles. You can do approximation of radiation. So what is coarsening, and which one of the coarsening is actually well correlated? Well, it turns out that nobody knows. And so we have a notion of low fidelity model. We have hundreds of choices, actually thousands of choices, right? And this is an interesting picture that shows a temperature field, a fluid temperature field. Again, is a vertical, so the particles starts cold and go hot as we go down. And this is the temperature fluid field, an instantaneous picture. And this shows the reference solution, the high fidelity, and 5 choices, right? And this is, just looking at them, you have no idea which one will be useful, right? Some of them look completely hopeless, LF4, for example. But still, maybe that's useful to get enough correlation. We don't know. Well, it turns out, as I said, we can actually build a number of those. We did a study where we actually considered 32 choices of these low fidelities. And I'm showing you here, again, just to give you a sense of how sort of even a simple process like Controlvariates, which is very, very well understood, when you push it in the context of such a complex environment, becomes a real challenge. So in this case, again, this 32, the axis here is in decreasing simulation costs. So what we would like to have is calculations here that are very cheap to do. So we can run thousands and build good estimate of the statistics, and then use only few of the high fidelity. And what I'm showing you on the y-axis is a measure of the quality of this simulation, comparing basically the average temperature at the outflow of this system. And if I show you the whole picture here, it's a big mess. So let me just tell you a few things here. Each one of these corresponds to 32 calculations, and they are compared to the distribution of the high fidelity. What we would like to see is a distribution in terms of the location of these points to be close to the high fidelity. But the other important thing is to say that the cost is actually decreasing by every time we move into one of these vertical bins is an order of magnitude cheaper. Okay, so effectively, if we could use simulations here, we are doing 10,000 simulations per each high fidelity calculation. So this is an enormous multiplier. And so obviously, if that's accurate, and you can see that some are reasonably accurate, then there is a tremendous advantage that you can take by doing Monte Carlo with the low fidelity and then just doing up sampling with just few samples on the high fidelity. So this is exactly what we did, and you know, again, without going in detail, so what? So what is that you do at this point if you can do Monte Carlo even with this complex simulation? Well, the first thing is what you said, right? You can build confidence intervals. So now we have temperature distribution that not only have a sort of a single point estimate, but they actually have, in this case, you know, 95% confidence intervals that we can build. And that's, again, just a way to convince ourselves that we're doing simulations that are now sort of a reasonable accuracy. But there is, you know, there is much more that you can get out of uncertainty quantification. And one of the most important one is what we call uncertainty ranking. As you saw even in this latest, you know, sort of final simulation, we had 14 uncertainties. Not all of them are important. So what we can do is to build, for example, a ranking and identify which ones are the uncertainty sources that contribute more to the uncertainty in the output. And again, statistically, this is a relatively simple thing to do, but it's very informative because also gives you actionable information. Now I know that if I want to do better simulation, I need to have a much better characterization of the spatial distribution of the radiation source, because that's a primary reason why I have uncertainty in distributions. Even more than something like absorption of the radiation in the particles, which, you know, seems to be intuitively the most important thing in the system. So again, this is a very high-level view, but at least gives you a sense of what we're after. Now, I thought I wanted to tell you a little bit about computing. So let me just very, very quickly say a few things here. I mentioned already it's an important piece of the Department of Energy process. And again, just to put this in context, the top supercomputer in the world, I don't know how many of you are familiar with the top 500, that measures every year sort of in certain metrics which one is the fastest computer in the world. The Frontier is the top one, has been for the last 2 years, is the first exaflop machine that at least is publicly acknowledged to be in this list. And it is a machine from the Department of Energy. So we do have access now to machines that are similar to Frontier. Frontier might not be available anytime soon, but these are machines that are already available. So the point though is why this is a big deal. Well, it's a big deal because computing at scale is complicated. We have known this forever since we started to do computations on parallel computers in the 80s. The way I like to describe it is this. I'm Italian, as you probably have guessed. So when we go from teraflop to exaflop, this is sort of what I'm looking at, right? If I want to compute or want to drive the 500 there, I mean, you just go and drive, right? It's not much you need to do. On a petaflop machine, you're already, you know, taking your risks, right? I don't know how comfortable you are driving that thing. I can guarantee you that if you jump on the exaflop machine, you're getting nothing. You're not moving, right? It's a real challenge to even extract performance. And part of the challenge is the interface. The user interface for these machines is incredibly complicated. What you need to worry about to get performance on those systems is much, much different than, you know, pushing the throttle on a 500. And so this is a real challenge for programmers and our, you know, students in computer science that have to deal with this problem. But, you know, the one thing that they will tell you is that computing is actually not the issue anymore. You can compute anything you want for free now. What matters is how you move data. So data, if the data is not in the right place, you're going to wait forever until that gets there and you get some computing on it, right? And so how do we deal with this at Stanford in this project is by working very closely with computer scientists on a completely new computing paradigm, which is, at least at Stanford, is called Legion. This is the system that we're developing, which over the last few years has become very, very popular. It's actually now a collaboration with NVIDIA. So we're hoping that eventually this will be available on all machines that run NVIDIA out of the box. And again, what is it? Well, how do you work on this? What is the difference? Well, there are a lot of differences, but the most important one, and maybe I'll just skip this and just give you this. The most important one is that we write in C++, just regular C++ with some libraries and so on. But there is no explicit data layout. We never declare an array, for example. That's a no-no if you want to make sure that your data is moving properly, because that fixes the use of the memory layout in a way that is very dangerous. So we never have explicit data layout. We don't have explicit communication. We never ask for an MPI send receive or whatever you're familiar with that moves information from one place to another. And we never have references to hardware. So we don't write GPU code. We don't write OpenMP. This is all sort of completely hidden by the user. So from a user perspective, this is great because they write C++. And then it's all the infrastructure of the computer science runtime, Legion, that takes care of it. Now, this would be, too good to be true. In fact, it's not quite like that. But, at least the intention is that there is a separation between who writes the code and what's the machine that is being run. And in fact, there is an optimization process that is used to actually extract performance. And it turns out that our code, this is the latest project we're working on, the exact same source code runs on CPUs and GPUs at very high performance. In this case, we're talking about fairly large calculation, 400 million grid points on the left and 2.4 billion on the right, on a very large number of GPUs, 512 GPUs. This is without writing CUDA, right? Which is pretty impressive. And the same code runs on CPUs. Now, obviously we're excited about this, but this is not sufficient. It turns out that most machines today have both CPUs and GPUs, right? It turns out that if you run on GPUs, you tend to ignore everything else because GPUs are fast, but you still have 40 or 60 CPUs on each node of one of these machines. So it turns out, we asked the question, can you use it for something? Well, it turns out in a system in a computer programming system where you can run the same code on CPU and GPU, you can start playing game and see maybe we can run GPUs, the high fidelity on GPUs, and fill the machines with low fidelity calculation on CPUs without really, much work on our side. The machine is there, it's going to be idle anyway. The CPUs are going to be idle. And it turns out this actually works. We can run on each node of, say, a Summit or Lassen supercomputer in this case, we can run up to 12 low fidelity calculation on CPU without slowing down the high fidelity on the GPUs. And this is run without having to do much. It's all managed by the runtime. And so this means that effectively the low fidelity calculations are free. They're not even inexpensive. They're basically free if you can fit them on CPUs that are otherwise idle. And this, again, from the point of view of uncertainty, is a great scenario, great opportunity. Last but not least is what we're doing today. And I'm excited to tell you 5 minutes about this, and then I'll stop. What is the project we're working on? Is a project that moves very far away from solar receivers. This is a compressible setting, a compressible combustion setting is a rocket at high altitude, so low temperature, low energy, low pressure. And the key innovation is that we want to ignite it using a laser. So we want to deposit energy very localized, very high amount of energy for a super short amount of time, and we want to ignite the system. And not only we want to ignite it, we want to ignite it with a given reliability. We want to know that it's going to be ignited, right? With a very high probability. So it's a complicated compressible flow. I don't have to go in details. Let me just show you how it looks, what it looks like. So this is the initial jet. Then at some point there is a laser pulse, and then boom, it ignites. Okay. So you've seen that we actually slow down the movie to show that pulse because it's a few nanoseconds pulse. So it's extremely fast and extremely localized high energy. And this leads to this scenario basically ignition. Now, why am I telling all this and what has to do with uncertainty? Well, it turns out this process is not very repeatable. So these are 8 calculations that are nominally the same, with the same inputs, the same ignition scenario, the same ignition source, and so on and so forth. But some of them eventually ignite and some not, two not, right? So in terms of reliability, this is to say that there is a 70% success probability in this case, which is obviously unacceptable for an igniter in this setting. So the question is, what is different in these cases? Well, the only thing that is different is the initial state of the jet, right? The turbulent, this is a turbulent jet, right? We have to ignite, the ignition is incredibly fast, but we still need to pick a moment, right? And if that moment is slightly off, just the stochasticity of the turbulent, the initial turbulent field is enough to not allow ignition. And if you don't believe me, this happens also in the experiments. So these are 3 Schlieren pictures of the same nominal setup. And even in this case, the time scales are much slower in the movie. Obviously, reality is Mother Nature time. But as you can see, not all of them ignite. One does not. Okay. So this is the problem. And now we have to figure out why is uncertain and what we can do. Now, one of the most interesting thing about fluid mechanics, though, about this problem is that we discovered, this was a real discovery from us, not for everybody, but for us when we started, that you can actually get ignition even if you put the energy source outside of the jet where there is no fuel. Right? You can imagine that, you need to ignite if you have enough fuel and oxidizer so that you have something to burn. Well, it turns out you can ignite even if the laser is focused on pure oxygen, like in this case, and it is also mechanics, is because that ignition kernel generates a jet that then pushes hot gases into the fuel and then eventually ignites. So it's what we call indirect ignition. And so that's obviously a much more complicated feature. So let me show you one-to-one what's happening, which is pretty cool. So this is actually the ignition kernel. Now you're starting to see the jet that is formed in the simulation is off the plane, and then it actually leads to ignition of these 2 cases. Now these 2 cases are synchronized, so you see how close, at least qualitatively, they are. Right? I was showing quantitative results before that. Now, and why does not ignite, right? Why this case is so finicky, why it ignites sometimes and does in others? Well, let me show you another, again, nominally the same, but with a slight difference, and this is what happens. Okay, so what has happened, and actually, again, simulation experiments are very, very close in this. What has happened is that at the very beginning, there is a slight disturbance in the core of this laser deposition. That asymmetry actually is enough to break down that initial jet, and rather than a single jet, you get 2 jets that are actually in opposite direction. So you get about half of the hot gases that are going in the wrong direction. And so the ones that are effectively hitting the fuel are not sufficient to actually ignite. And this is, again, just sufficient at the beginning that there is a slight difference, a slight shear in that interaction that is sufficient to basically give a completely different outcome. So this is, the problem we're working on. We're still at the very beginning, but it is, quite exciting to sort of having to work in this setting on these machines with this kind of focus on certification. So let me finish by just saying that, obviously went super fast and hopefully at least you got the sort of big elements of these projects that are quite exciting. There is much more that we're doing in the center, including sort of new topics like machine learning and data analytics and so on that I haven't had a chance to talk about. I also didn't have a chance to acknowledge everybody that works in the center, which is a very large group of really creative and talented people. So I point you to the website if you're interested in CMA, is the Italian word for ensemble. All these simulations are ensemble of many, many simulations. And so that's the name of the center. And with that, I'll thank you and thank you for your attention. And if you have questions, I'm happy to answer.
Any questions for Gianluca?
Yeah.
Great talk. I was curious about Yeah, the different aspects of your center you're talking about. The one thing I was curious about was how do you come to decide what's the next scientific challenge you're going to do, and how do you then decide what the experiment is going to do?
It's a great question. So just to put this in context, we are in the second year of the project, and there is already talk about the next phase, which is 4 years, 3.5 years ahead. So it takes a long time. What we do at Stanford is that we just sit down in a room and we brainstorm. And I can tell you there are a lot of crazy ideas that people come up with. We typically don't start from, can we do the experiment? We start from, what is the craziest thing we want to do and why? And as I said, most of the time, the ideas are just too crazy to even start thinking about it. But then once we start sort of down selecting to 3, then the question of can we actually do an experiment becomes critical. So although it's a purely computational program, in fact, the Department of Energy would much rather not even fund experiments during this program. We do start from the experiment as soon as we sort of narrow down the scope. And in this case, the experiment, the last one I didn't mention, the experiments are done in Purdue. So these are not experiments at Stanford. We don't have facilities or rocket facilities available. So we partner with them and they're doing all the experiments. In the previous one was John Eaton in his lab doing it. So we are trying to be open to collaborations if needed. But the experiments is a critical piece of deciding the problem. Thanks. Yeah.
Yeah. The Legion framework that you mentioned, is that similar to what kind of the OPC from Oxford is and PyFR does, where you basically as a user just put in your governing equation and then it's all translated into?
Actually, no, not really. So it is really the programming model is just C++ with some constraints, I would say. So, but you have to program them. So you basically write your code more or less like if it was a sequential code, but you have to write it. So all the algorithms, we don't work at the level of the operators. You have to write the actual algorithms. What the system does is that it's mostly about the analysis that goes on. So you write a set of tasks, then the Legion framework decides or learns what data each task requires. Right? The data, you're just explicitly saying this task requires this quantity in input and this quantity in output. That's it. Right? Then the runtime understands who is using them and who else needs to use them. And then based on that information decides how to structure the communication. And so I know that is generated by the code automatically. But the actual algorithm discretization method and so on is all done, basically in a C++ infrastructure. It's not in an abstract sense like in some of the other. It's not the only system that works this way. There are, you might be familiar with Cocos, for example, from Sandias. So there are a few other frameworks like Legion, but it's not very abstract. It's actually it's very expressive. You have to write basically the entire code. Just don't worry about communication or things like that. And it's an open source, I should have said. Legion.stanford.edu is open source, and if there are tutorials, it's actually in reasonable shape. Hopefully, if NVIDIA keeps investing in it, it might become maybe proprietary at some point, but at least it will become more professionally maintained. At this point, the support comes from graduate students, and they tend to be busy at times. So it's a little bit complicated to get help. Yes.
We made sort of various attempts to go on graphics cards and get the performance, but we were always bogged down by the fact that we work with structures of arrays, sort of arrays of structures, as opposed to the structures of arrays. So in that sense, if you, you then have this problem that it's not so easy to get that sort of gain on the parallelism. But I guess the argument you're making is big that even beyond that, the key issue is really the data throughput. Absolutely get the data, and that's what we observe.
It's 100%, and it's such a shift from even the time that Andrew and I used to work together, where you were trying to save computation as much as you can, right? You will just reuse things that you're computing. That's completely wrong paradigm these days. It's all about data, and then if you need to redo computations so that you don't ask stuff in memory, that's great. Just go ahead. So it's all about data movement, and in fact, this Legion they call it a data-centric programming system, really because the idea is that everything is around data and how data is organized. And one thing that I didn't mention, but I do want to mention, is that we as sort of traditional computational scientists, computational engineer, we end up being pretty good with programming on different architecture, parallelism, distributed computing. But the truth is that the new machines have 5, 6 types of different memories. Right? You have memories for the GPU, memory for the CPU, memory that is common, memory that is more long-term. We have no way to express that in our codes. We just don't. So this is left anyway to a compiler or some sort of optimization that occurs behind the scenes. And this programming model actually takes that information as a primary information. That's the first decision. If I'm using that data, where is that data? What kind of memory should that data be so that I can get it quickly? And that is all before even thinking about how big the task is in terms of computing. That's the first decision that is made. So it's a pretty, it's a very different way of thinking about computing these days.
Is it helpful to use sort of meta-template programming approaches in this, or does this just get in the way?
Yeah, that's a good point. What you want to do is to make sure that the programming model runtime has easy way to understand what's happening in the code. So the more the code is obscured by perhaps complicated structure and so on, the more complicated the analysis is, and sometimes it just doesn't work well. So typically what we do is to write the simplest possible codes, but in some cases you need to use templates, but most of the time we try to make it as simple as possible so that it's easy to analyze. You have to think of these as right now compiling a code takes some time. For us, we compile even if we just change something like the grid that we're using. The code is recompiled, and that compilation takes quite a bit of time. So these are important decisions because it's a very different computation if you run on a certain grid or a grid that is 100 times bigger. Right? That makes a lot of different decisions in the actual code that is sent to the hardware. So,
Gianluca, I think there are some questions online.
yes.
So if someone has a hand up,
Oh,
maybe
That's me.
yes. Hi.
Hi. We just had I'm more interested in the experimental parts that you had in the slide just before this, where you had the ignition failure.
Yes.
I was just wondering whether you have the splitting of the jet always in that particular fashion, because the slide before that, when you show that the slanted position of the jet, I thought when the jet splits, you would have the opposite of what you see in the Schlieren, of what it is right now.
So the short answer is no. The type of failure, there are different types of failure. It depends very much on the underlying flow field, what the flow field looks like when the ignition, where the kernel is deposited, laser kernel is deposited. It turns out, in fact, in other, and we have, I think, literally 250 shots, so that there is a very large variety. In some cases, we see a drifting of the kernel rather than this sort of splitting of the jet. So there are different scenarios. We're still sort of early in understanding all the possible pathways, but there is definitely more than one to failure. The success is really just measured by how much hot gases can get close to the stoichiometry, to the right stoichiometry. So that's when you get success. How do you get there doesn't really matter as long as there is enough hot gases, but then you can fail in a number of different ways. I think that's
all right. So that's just one of the failure modes, not
that's right.
Okay,
that's
so,
right. Unfortunately, that's right.
Yeah. All right. Thank you.
Yeah, maybe one last question.
Thanks for your talk. Your last project about rocket jet reminded me a bit about auto ignition in engines, where maybe like 5% of cycles may auto ignite, or maybe 5% doesn't ignite at all. And if you're moving towards a more simulation-based confidence. How, without an experiment, how do we, I guess, use simulations to predict these sort of transient things when sometimes they're quite rare, but can be very damaging?
Yeah, this is the whole problem. So the first thing is to understand why there is that stochasticity, what are the possible sources, and in many cases you have to guess. You don't know, right? What exactly is happening. But then, especially if the failures are rare, you need to run a very large ensemble of simulations to even capture them, right? And so the question becomes, you might not even be able to afford it. So methods like the one that I was sharing, sort of the idea of multi-fidelity and so on, is a way to drive perhaps the exploration towards regions that are more interesting from a point of view of failure. It's not that we have, a magic way of actually identifying what's happening. The only thing you can do is really just being careful in exploring all the possible uncertainties. And again, from a simulation perspective, the challenge is that you make assumptions in the modeling that you're using, and sometimes those assumptions are the most important in terms of what happens, right? And it's not obvious that we have necessarily a better way to model the system, but sometimes the limitation becomes exactly that. In an experiment, at least it's Mother Nature that you're looking at. In simulations, you always have assumptions, and that it's difficult to capture. Now, just to give you a context, and then I'll stop. We don't have auto-ignition here because the system is a very, very low temperature, very low pressure. So if you don't do anything, it's not that just mixing oxygen and methane will lead to combustion. So this is a case where the conditions are such that you need an external source to actually ignite the system. And so the hope is that you can be intentional enough that you actually always have ignition because you're controlling what you're doing, right? It's not in an auto-ignition sense, there will be a much more stochasticity in the system that perhaps you cannot control. Here, the idea or the intention is to control it completely. So eventually be, maybe not 100% success, but really a very, very high percentage of success.
All right, John, one last question. Sorry.
I think it's such a great opportunity. It's so holiday mode, so it's so good to have these conversations. But I wanted to ask you about extreme events. Because if you go to the high fidelity simulations, you have a greater chance to see the emergent behavior. And very often, the whole jet may blow up. And you might get that. And in physical experiments, that happens, let's say, classical experiment done in the Technical University of Stuttgart 20 years ago. They had this little vulcanization kit for tires. They just started to burn it and dropped it into some tank, into a barrel full of water. Most of the cases, it just gets squashed. Right. That's the end of it. Every 100 times, the whole barrel just explodes. And so these kinds of things.
Well, I mean, as I mentioned before, though, you have to remember that these are simulations, right? So emergent behavior might be part of the simulation if you're able to capture it, but it might simply be out of it because you made assumptions. So at least in our setting, as I said, we are not really looking for a stochasticity that is sort of emerging in terms of dynamics. It might happen, and we might end up seeing it in the experiment. But what we are trying to do is to really build a system that is highly controllable and try to understand what are the pathways to failure. For us is a way to identify ways to control the ignition. Just to give you an idea, one of the things we are trying right now is that rather than one pulse, maybe you can have two pulses, right? And the way they interact with each other is such that they overcome some of these initial stochasticity. But that's sort of eventually what our goal is, not to again, the idea is to have a controllable system in principle.
All right, I think we should start. I'm sure Gianluca will be here for a little while longer if you want to have a chat with him. So thanks. Could you join me again? Thank you.
Thank you.